Welcome to Drone System and Control course. Today we are going to talk about autopilot design. Okay. What are the objectives of today's lecture? Autopilot system architecture and components. See, when we talk about autopilot, which is the brain of the entire drone, how the system need to be architected, because we need to understand, we need to communicate to the drone, whether it is operating in autonomous mode or semi-autonomous mode or a manual mode. When you are talking about a manual mode, you are just communicating with the drone to give commands, right? So how the system architecture need to be connected, how the data will be communicated, how the fail-safe operations will be taken in, all these aspects we have to discuss in this particular module, right? Second is functional requirement of autopilot. What exactly we expect the autopilot to perform? One is to provide automatic controls based on the inputs that what we provide to the system. Second, we also expect some functional aspect of it, like auto takeoff, auto landing, pre-program, pre-fixed maneuvers, safety checks, and what we call as operational limits. All this, how we enable it, how they interact with each other, is a functional requirement. Another interesting aspect, when we talk about control system design, what comes to us is, let's say if you are just going to buy a lift for your own home, you need to look at the functional requirement. What is that functional requirement? The lift should be safe enough to operate. Lift should not provide any uncomfortable feeling when you are just going from one floor to another floor. It may be a 1 floor above or 10 floor above, 20 floor above. The rate at which it just moves should not accelerate so fast or decelerate so fast. It has to stop at level at the floors, right? All these are requirements. But those requirements cannot be taken in as it is. There is a need to convert the functional requirement to technical requirement. For example, if we say that it has to stop on the same level, we are talking about steady state error should be 0. Once my level is detected, first floor level, right? First floor is 1 meter away from the ground floor or 2 meter away from the ground floor. The lift should stop exactly at 2 meter. It should not have overshoot. It should not have undershoot, right? And you want to have a lift to go smoothly to the one floor to another floor. It should not have an oscillation, right? So you see, the requirement of passenger comfort need to be translated into technical requirement and functional requirement, right? The same way we need to convert the operational requirement of the drone, right, into technical as well as functional requirement. In this lecture, we'll talk about more of functional requirement aspect of it, right? Then comes whole system architecture. What sensor we are going to do? How the sensor data is going to come? If the sensor data is not sufficient, how are we going to estimate the other states of the system, and how the estimated state is sent to the control architecture, how the control architectures are connected for a different modes of operations, right? Different functional requirements of the autopilot, how these flight control system architecture are going to vary. That aspect also we have to understand. Then we have to understand the core of the control system design. What is going to be the innermost loop? What is going to be the outermost loop? Right? How this is going to be connected, and how the flight autopilot is going to be architected in such a way the low level controls that what we are going to implement is going to satisfy both our functional requirement as well as technical requirement, right? So we need to understand the whole loop. Once the control produce an output, what the control will say? I want U1, U2, U3, U4. U1 is going to be my thrust. U2, U3, U4 is going to be how much my pitch and roll and yaw I'm going to have. But I cannot directly give the thrust to my rotor. For a quadcopter, you have 4 motors. For hexacopter, you will have a different number of motors. Octocopters, we have a different number of motors. You may have a tricopter, right? So how are you going to convert the input to a control? So control allocation is a very important aspect of it. How we are going to do the control allocation is also a factor which we need to look at in the system architecture, right? Now, let's look at what we are interested in. We are going to design an autopilot that allows a drone to fly either autonomously or semi-autonomously. We'll talk more about autonomy, different level of autonomy, when we use the different levels of autonomy, what is the relationship and all that in the next module. Okay, but at this point of time, if I want a drone to fly autonomous, I need certain features to be there, right? First, I need to make sure my flight control architecture just to stabilize the drone, right? And it has to maintain desired altitude, desired heading, desired speed, right? Suppose you are planning a mission, you want to go from A to B. First important thing is you need to say you have to climb to a safe altitude. Then you can follow the waypoints and reach the destination and descend to a safe altitude and land. Right? Now, this is my mission profile. Technically, what we are talking of is I'm taking off from a point A, going up to a safe altitude. This is my H, and then I'm traversing to some other point and landing to this. Let's say this is my mission profile if I'm talking of. What's more important is what is my H to which I need to climb. What's the altitude I need to maintain when I go from point A prime to point B prime? What is my H? What is my velocity? Right? What's my velocity? Both are important. What speed I want to go, right? At what speed I wanted to descend? What is my descent speed? What is my climb speed? Right? These are important. Depends on type of payload that you carry. Your descent speed may be different, climb speed may be different, right? So if you are emergency, what is the speed at which you are to operate? So we have to follow the commands accurately. So I need to get my architecture in such a way I can follow the command accurately. Either it's a semi-autonomous mode or fully autonomous mode. Fully autonomous mode, I should be capable of generating such commands so that I can land. I need to follow the predefined dynamically computed paths too, right? Either in this case is more predefined, right? This is predefined. I'm just saying this is what you should do. Suddenly, let's say there is an obstacle comes here in this region. I cannot follow this path. Then I need to do a dynamic path and come like this. So in such cases, I should be capable of generating this path, and I need to follow the path accurately as possible. When we go into navigation lecture, we'll talk more about obstacle avoidance, and in autonomy we'll just dwell in details about how do we do that, whether the obstacle is static or dynamic, how this path could be computed. But at this point of time, my architecture should be capable of either follow the predefined path or should be capable of generating path on board and follow it. That's very important. Right? I should be able to execute missions like surveying. When I talk about surveying, let's say I'm just looking at an agriculture field. Let's say this is my agriculture field, right? I need to survey this area. I could have certain length, certain width, right? It could be in few kilometers. But I want to survey this area, means I want to map this. So I may have to do the motions raster scan, right? I should be able to do this. Right? Or I may have to go from point A to point B and do the delivery. Right? Or I may have certain object. It could be a tall tower. It's a building. Right? And if there is a building, I need to go to a certain height and do the inspection. Right? So what is more important here is how we are going to use, and in such kind of requirements, we need to convert this mission into desired altitude, desired heading, desired speed or desired trajectory to be followed, and how this control architecture taking care of all of this at the same time, very important component of can you maintain the stability of the drone. No matter what wind, right, what happens, the drone should be stable. Right? So it's very important to understand this in this lecture. Right? What I mean, certain functions, right? What I mean stabilize means maintain the orientation even under the disturbance, right? So what, let's say you are hovering, right? I'm in a stabilized mode. what I am expecting? Aircraft should be hover, right? It can drift. It need not be holding the position. It can just move. But it should not climb up or it not descend. It can move in XY plane. I am okay with that. It has to maintain the stability, whatever the wind condition is. If I say altitude hold, not just hover, it has to maintain the altitude, right? H should be constant. Then if you say loiter, right, around a position, it could be a position X, around that position you could keep going in a circle, or you can go in a rectangular pattern. I wanted to do that, but I want to hold the position, say. So I'm very important there. Waypoint navigation, I can just say go from one GPS location, right, location 1 to another GPS location. I can specify in a global reference frame, you are here, go to from Bangalore, from IISc to Yeshwanthpur, right? I can specify point A to point B. Those GPS location I can provide. What is the latitude, longitude and altitude, and say you have to go to another latitude, longitude, altitude, you should just go there, right? Suppose something happens. I want the drone to come back, what we call return to launch point, wherever it started, right? Something happened halfway through, I'm not able to complete my mission, I want to abort my mission. What will I do? Shall I land there or shall I come back to the starting point? That's what we call return to launch. You need to understand the functions and how the functions is going to be transferred. See, suppose you travel from a point A, go to certain height and travel halfway through, I'm aborting a mission. Then the drone has to come back to the same point and land, right? So this function is very important. What kind of fail-safe that we can provide? Suddenly I am seeing that it started maneuvering very aggressive, closer to a target. I should be able to abort the whole mission. I should be able to kill the drone so that what I meant kill means I just have to stop functioning of the drone. I need to stop the motor so that there is no thrust. It just falls down rather than going and colliding with another target or another environment, right, where I don't want to create a damage, right? So we need to see how the fail-safe function is going to work. When there are important, I'm not able to see it, I can see through a camera, then we are talking about beyond visual line of sight, or I'm talking about RC signal comes into picture. How am I going to handle that? These are all important factors, right? Now, let's look at certain components of the whole thing, right? Flight control system is a very core component of the autopilot, right? It's basically a brain of the drone, okay? It's going to perform some control loops, right? Basically stabilize the vehicle, follow the speed command, follow the altitude command, follow the position command, or follow the trajectory, right? That control loop is going to be done here, right? It could be either PID based, right, proportional integral derivative, or modern controls like LQR, or I can go with model predictive controls, right, more robust control systems. I can use any of these to achieve what I want, right? I converted the mission requirement to a functional technical requirement. Basically going to a specific altitude, H, at a rate at which I want to climb, 2 meters per second, which is going to be comfortable. Then I'm giving a speed command, vertical speed command of 2 meters per second. So you climb from ground and reach that particular altitude. When you reach the altitude, you stop and you maintain that altitude. If you decrease, you give more thrust. If you go up, reduce the thrust so that you maintain the same altitude, right? So that's where this commands will take care. So we convert the mission to a technical requirement and forward the technical requirement to your control loop, and the control loop will execute it, right? We'll understand it in a little bit more details when we move further down, right? Now what we need, I need a sensor. The sensor need to tell me, right? I have a sensor which is inertial measurement unit. We talked about sensors in the earlier module, right? What are the different sensors are there? I have an IMU, which is basically an accelerometer and gyro integrated together. I'll be getting it from all the 3 axes, right? I'll also have a magnetometer. The magnetometer will also give me the heading of this particular drone, right? So I can measure the acceleration and I can measure the angular velocity. With acceleration, angular velocity, we talked about estimator, right? Kalman filter, extended Kalman filter. We can use that to estimate what is the position, what is the velocity, right? What is the attitude of the vehicle. All that we can do. Then we have a GPS sensor. GPS sensor provides a global position for data for navigation purposes. I get the position, I get the velocity also. I can fuse this with IMU, right? I can also have a barometer. Barometer will gives me an height, or I can have a single point lidar. I can have a radar to get my height. So I can fuse all these measurements to get the state of the current drone, right? And I need an actuator mechanism. Right? My electronic speed control system basically takes care of command coming from my brain into electrical signal so that my motor can start changing the RPM, so that the change in thrust and the change in thrust will help me to achieve the desired trajectory. Right? So this actuation mechanism is also very important. We talked about all this in the earlier module, right? The actuation mechanism talks more about how the control allocation should take place, right? That we will discuss in this end of this lecture. The software stack is also very important. It talks about real-time firmwares like PX4 or Autopilot that we need. We talk about the requirements of this autonomy software or flight control software when we go into the last module on autonomy. We talk more about it. Ground station interface, right, where the you could have a queue ground control or a mission planner where you can provide your functional requirements and safety and everything, and that has been translated into technical requirement and stored in our autopilot, which is a brain, and which execute that, right? So there is a connection between these two. High level planning and all this you do it, but then waypoint navigation is has to happen in the brain. Obstacle avoidance have to happen. So only these sensors are not sufficient. You need an additional sensor. You may need a camera. You may need a lidar. You may need a radar. Right? We need all these sensors to see what? See my environment. Okay? Whether my environment is safe enough for me to operate. So that level of autonomy comes in. We need to talk about obstacle avoidance and all this. In module, next module, navigation module, we'll talk about obstacle avoidance, path planning and all this. At this point of time, that module have to run in my brain, and that need to generate the trajectory, and that trajectory we will use for the drone to follow with the inner sensors, IMU, GPS, magnetometer. We'll use that to follow those target trajectories, right? Let's understand further on the control loops, right? How the control loops are there. There are two loops are there. One is the inner loop, the other one is outer loop. Inner loops takes care of basic attitude control, right? Basic stabilization aspect of it, right? What happens? I'll just make sure the pitch, roll, yaw attitudes are controlled. Right? So how does it work? I have a drone. I take the states through my sensor, and I have a fusion, basically extended Kalman filter or something, which will be estimating the states, and that states goes to my attitude control. You could get it desired attitude either from a user directly, right? Or it could be coming through my position command or velocity controller. That will give the desired attitude, and desired attitude and current attitude, that's the error that I wanted to reduce it. My flight controller takes care of it, right? The control system what we are developing is going to take care of that. It could be PID control, or it could be a pole placement. We could tracking control mechanism. We can, or model predictive control mechanism. One of that will take care of it, right? And that it will produce necessary control inputs required. That control inputs need to be translated into RPM requirement. That will take care in control allocation. This control allocation matrix, it depends on what kind of system that you are using. If it's a quadcopter, it is different. Hexa, octa, it will be different. We also get the desired thrust thrust information directly to control allocation. Right? So you see, this is the inner loop part. What you see in the red line is the inner loop part. The outer loop is more into automatic aspects of it, right? Altitude hold, position hold, trajectory tracking, all that will happen in the outermost loop. So innermost loop operates in much higher frequency, control frequency, so that you can stabilize the aircraft. Outer loop happens is lower frequency. We'll talk about it all this in little later in detail, right? For attitude controller or position velocity controllers, we can use different type of control system design, right? We can go ahead with PID, what is proportional integral derivative control, which is commonly used in most of these systems, or you can go with more advanced mechanism like a model predictive control, which takes care of uncertainties and everything. And then you also have something called control barrier function, which is sitting in the outermost loop to take care of the safety aspect of it, collision avoidance aspect of it. We will read this particular aspect more in navigation lecture and also in autonomy, right? But at this point of time, I am introducing this for you to understand there is something which is present in my brain which can generate the trajectory such that the drone is always safe, right? Or I can have a learning based controls, right? I can adapt, right? I can adapt to the changes that is happening, and learning based control can also be implemented here, right? Let's get more details into what are the different components of autopilot, right? The system architectural level of it. Let's look at the software aspect, right? I mentioned earlier there is a ground control system. That's a Q control system or your mission planner, right? The ground control system, what is that it's going to do? It's going to help the user to provide the mission. You can say, I wanted to take off, go to an altitude of 100 meters and then follow the waypoints 1, 2, 3, 4, 5, right? And land to the location in the fifth location, and while takeoff you go at 3 meters per second, while moving from waypoint to waypoint 2, this is the speed you need to maintain. You can specify all these, and this is where you will be transmitting the data from your control Q ground control to your brain. The drone will also transmit its current state to your ground control system. Ground control system will just provide real-time position of this drone in the map for you to see whether it is really performing what it's supposed to do. That's one software itself, right? Then you have another set of software where you have a drivers. Drivers basically needed to connect your sensors, right? You have IMU, you have GPS, you have a barometer, you have camera, LiDAR, radar, and your motor control. All that requires conversion from your flight control to digital signal, and which goes to the electronic operation. And convert from that into an electrical signal and send it to the motor, or getting an analog signal. And you have ADC which converts into digital, you need to read, you need a specific communication mechanism needed. Those are the drivers we are talking of. Then you have a middleware, right? If you are talking about autonomous drone, where we'll talk more about it, there's a middleware which talks how it's going to enable the communication, right? How am I going to talk to the particular autopilot? Am I going to use Mavlink protocol to communicate, right? I need to talk to him from ground station. When I say what I meant talk to him, I can give my remote control inputs. Suddenly I am seeing some disturbances, I want to take over. How do I take it over from the remote location? That's a very important aspect we need to look at. Or if I am talking about RTPS kind of a thing, or UR, it's a different software that is helping us to the higher level autonomy layer or functional layer to talk to the flight control input, right? Those are softwares which we need to understand. Then you have a modules, command module, navigation module, control module, log modules, different modules are there. You need to store the data internally. Once it lands, you can recover the data and analyze. You need the loggers, right? You need the controllers, you need the navigation mechanisms. All these are mandatory. That's a software aspect of it. Now when it comes to hardware aspect of it, the brain of the computer, your flight control hardware, it could be a microcontroller, right? Which runs on real-time operating system. This is where all your control decisions, everything is going to take place, right? The flight controller need to be connected to motor for actuation purpose. It has to be connected to a sensor to collect the data, to understand the current state of the drone, both internally and external observation, basically the environment that I need to get to know. All that is the sensor. You may have a certain payload, right? Suppose you want to deliver something to a point, right? Once you reach the point, you don't have to go down, you can drop. For that you need to again command to that payload to do something. Or the payload could be a camera itself, where you wanted to image something, inspect something. You want to perform some actuation. That is also connected to your flight control hardware. This is on what action that you perform, what observation that you do to the environment. In addition, we need two other things. Communication is very important, right? There are two types of communication. I can send my data, that's what we call telemetry radio. I send my current state or current situation of my payload, everything to the ground station. This telemetry radio is key for data to go out from my brain to ground control system where the operator can see it, right? Whether you mode it in, you fly it in semi-autonomous or autonomous mode or manual mode, you need this data to know what's really happening, right? Then you have a RC radio also is available where you want to command, right, to that particular drone to do something else, right? You want to alter the mission, you can command through your RC radio. That these two are communication interfaces which also happen to your flight control, right? Now let's understand a little bit more details on how the mission computer going to be. This one is for semi-autonomous mode, but once you have a mission comes into picture, autonomy comes into picture, how the system architecture going to differ, right? My ground control system will not change. Software level, if you see, drivers remains the same, middleware almost remains the same, modules will remain the same, software side will not change, but in hardware you have one additional processor comes into picture, what we call mission computer. It could be your RPi or it could be NVIDIA GPU systems, or it could be your SoC systems. These are going to play an important role. These are like a mission computers, right? These mission computers going to play decision making capability when you are operating the drones in autonomous mode. Now we need to understand how they are connected between each other, right? My motor and sensor will be connected to my flight controller, right? You see earlier the payload is also connected to flight controller. Now payload is not connected to the flight controller, payload is connected to my mission. The mission computer decide what to do with the payload, right? Mission computer have its own sensors. It want to see what it has to do, right? So those sensors, it could be a camera, it could be a LiDAR, it could be a radar, right? So it will see the environment and decide what to do with the payload, right? And it also have a connection to a telemetry and earlier flight controller was connected to telemetry and radio, whereas here it's telemetry and radio communication happens to your mission computer. Your mission computer command your flight controller what you want, right? If I see an obstacle through a sensor, let's say by camera seeing an obstacle which is moving at 2 meters per second, potentially I can collide with him if I continue in my same trajectory. Your mission computer generate change in trajectory. The new trajectory, right, will be sent to your flight control hardware. Now flight control hardware will take care of following the new trajectory, right, and return this information back to your flight controller. Sensor information will come, so that mission computer knows what is the current state of this vehicle and it act accordingly, right? So This is how your system architecture going to be, right? Now let's do a little bit more details in Autopilot system architecture, right? We talked about these middlewares. What are these middlewares? The device drivers for embedded sensors, right? Or communication with external world, a companion computer or GCS, RC, all these required some kind of interfaces which can communicate with this external system, right? Or you are publish subscribe message bus, where I can publish my data or I can subscribe to a specific data bus and read data from there. All that is going to run in your middleware, right? And then you also have a simulation layer to control computer modeled vehicle, right? So what I can do is I don't have to fly the vehicle to verify my algorithm. I can still use the middleware. I can still use my brain. My brain runs the decisions. The output of it, I can take it from the middleware, send it to my simulation engine, allow this dynamics to simulate the motions of the vehicle, and the motions of the vehicle I can just pass it back through middleware to my flight controller, right? And I can verify whether my flight controller can really perform or not. It's more like a hardware in the loop simulation, right? So that's where the middleware plays an important role. If you look at different systems are there. Different systems runs at different rate, right? Different runtime requirements also, right? We need to understand that. Control messaging update, right? Basically I need to get the attitude loop, right? So innermost control loop. I'm going to take it from IMU. I'm going to sample the IMU at 1 kilohertz, right? I sample it. I filter it out because IMU could be noisy. I filter it out, but I may have to publish my output in 250 hertz so that my control architecture take this information and do necessary actions. Then you have outermost loop, which is basically a velocity control loop, right, which will run at 50 hertz. And then you have a navigation loop which runs in 8 hertz, right? Depends on how you interpolate the data. Sometimes you run it in 1 hertz also, right? So these are different update rates going to be present in my Autopilot architecture. So I have to understand, for some sensor my sampling rates are different, right? Some sensor my sampling rates are different. The rate at which I publish is also different for my control loop. So these are something is required when you are designing your architecture, right? Understand what is the system frequency, how we have to read this signal and how we have to send it to, so that how fast my motor can act, right? All these are important factors, right? And all these have to run on a microcontroller. The runtime environment is also important, right? I can run it in Linux, or I can run it NetX and QRT, right? These are like RTAS, real-time operating systems, right? So I need those. I don't need an unnecessary control in my operating system. It should be real-time, right? We are talking about a system which flies very fast. So I want to take care only those stuff. Dedicated architecture, what we call, right? Specialized architecture, specialized computer. They perform only specific task. That's what we will be using in our flight controller, right? Autopilot software architecture. There are some aspects we need to understand, right? The message bus. The message bus sends some informations, right? It can send information to external connectivity. It can send information for data to be sent out. It could through Mavlink or UART, UDP. I can send data out. I can send data to my drivers, right? Or I can send data to my main input like RC, or IMU. I can send it to airspeed. I can send to telemetry. Sometimes I can just connect optional sensors like optical flow or GPS, gimbal to control my payload or control my camera, right? I'll send signals there. I'll also send signals and receive signals from flight controller, right? I can look at the state machine, basically different modes in which my flight controller is operating. I can change the mode. So I send it in autonomous mode. Suddenly I realize that it's not performing what it has to do. I want to take over to manual mode, fly by a remote pilot, and bring the drone back home safely or land safely, right? I can look at the current state, I can modify the state of the whole flight controller, right? Which means I can enable and disable different functions of my autopilot, right, using the message bus. I can handle the RC, I can look at the state estimator, I can change the controller gain. See, sometimes the pilots are different, but system is the same. Some pilots understand the stick differently, right? He wants some aggressive. It's like this: when you take a car, somebody will just drive it normally, somebody will drive it very harsh, somebody will drive it very slow, right? So I can change the gain based on users expectation, right? Users reaction time. So I can control that also. I can control the controller gain also, flight controller gain. Suddenly I see that it's not performing, I wanted to update my controller, I can update that. I can control allocation also we can change. Suddenly there is one rotor fail, one motor is fail, right, in hexacopter and octocopter. I can change the control allocation such that the aircraft still perform what we need. And also I need an output driver. Those buses also need to be connected. We also need to connect to databases like what is a mission, what kind of fence we are talking about. Geofence is basically you are talking about the limits of operations. What are the parameters? And we also have to write all the data into a memory, right? The logs, the current state, mission plan, what is the current performance, everything can be logged, right? That's the message bus architecture you will have, right? Let's dwell detail into functional requirements of it, different modes of flight, right? We have a stabilized mode, we have altitude mode, we have a position mode, we have a trajectory mode. Okay. Stabilized mode, if I say, it's a basic mode of flight, right? It just makes sure that the aircraft is stable. Basically control only, the pilot is responsible for controlling the drone. Autopilot only assists the pilot by maintaining the stability, right? The innermost loop is functioning, the outermost loop control is given to pilot. Pilot is responsible for everything, right? If you say complete manual mode, not even having stabilized mode, even there is no stability loop, full control is given to remote pilot. That's a level 0 autonomy. We'll talk more about those when we move on to autonomy module, right? Now RC stick, basically the pilot stick is responsible for pitch, roll, yaw, the level automatically, right, if pilot leave the sticks. So what is happening here? The pitch, roll, yaw is controlled by him. He leaves the stick wherever the attitude is, whatever the attitude, it just comes back and stays there, right? What is required? The thrust command sent directly to the control allocation. There is no vertical velocity control here, no altitude control here. Whatever the stick command which goes directly to the control allocation. You should have at least 50% stick to maintain a altitude. If you see a drone coming down, you may have to increase the thrust to increase the altitude and maintain. So pilot have to do lot of workload to maintain the drone in specific position, right? We will study more about different modes, altitude mode, position mode, trajectory mode in the next lecture. What we did now is we understand what is the overall architecture of autopilot, what are the different modules present on the flight control architecture, like you have the software, you have the hardware, you have a different software for flight controller, for mission planner, hardware, how it's connected, what is this functional requirements, how these are integrated, we saw in the current lecture. Okay, thank you.